So I'm going to talk today about the past and the future. We're going to do some math and we're going to do a bunch of data. But for right now, let's just take, before we get started, let's just take a moment and observe how we experience the past and the future. If I clap and it recedes into the past, we get almost a spatial sense of the past time that follows us around as we go about our lives. My lab has spent a lot of work studying that over the last decade or so, and we've begun to make some progress in really getting an understanding of that. But watch this. So if I go A, B, and then I do it again, I go A, B. And let's do it one more time, and then let's pause after A. If I go A, and so let's stop. So we have a sense that A is in the past and B is coming towards us from the future. We're able to predict, because I said it like twice in a row, that B follows A at a lag of like 4 seconds. And in the moment as A recedes into the past, we simultaneously feel as if we have the experience of B moving closer towards us. At least that's my experience. And your mileage may vary, and we're good scientists here, so we're not going to rely on our intuition. I'll point you to an experiment that we did that directly evaluates this. It's should be online in JP General right now. We compared a well-known judgment of recency task in which we asked people, and this has been studied since the 1980s at least, in which we asked people to judge which of two probes was closer to the present after following a list. And we observed on the left-hand side classic results, and I can walk through this if you're interested, but just read the paper. Anyway, that's how memory for the past works. It behaves as if there's a timeline. The models people have developed for that are very much like visual search models developed by Ann Treisman and others. But rather than searching over a visual display, looking for a target, it's as if you're searching over time, and we've known this for decades. On the other side of on the right-hand side of the figure, I'm showing you analogous results from an analogous experiment, in which we asked people, we gave people a predictable future. We gave them a sequence that was predictable. We gave them 2 probes and asked them to judge which of the 2 probes was going to happen next. And people behaved exactly as if they were searching along the future as well. So perhaps this intuition that we carry along with us, an organized timeline of the past and an organized timeline of the future, perhaps this is non-crazy. So the goal of my talk today is to try and begin to describe how we could build that future. So the short answer is, well, we have this memory for the past that we've spent the last decade working out, and we feel pretty good about. The short answer, in case I run out of time or things go entirely off the rails, the short answer is that you construct the future by noticing the associations between the past and the present, and then you use that to infer. Knowing the present, you can then infer the future. So that's the idea. So about 10 years ago, my colleagues and I proposed a mathematical model for how the brain might remember the past, very much inspired by data from neuroscience and psychology, and the intuition that we did with the clapping experiment. And the idea goes something like this: that we have a veridical past at each moment. At each moment t, we have a veridical past, f of tau, where tau is a timeline going from the present back towards the past, and that we maintain a representation something like and so the past is something like a musical score. There's a record of what happened when, which note happened at which point in the past, and the idea is that the brain ought to construct something like a record of that memory that has some ordered dimension, f tilde of tau star, where tau star is my internal estimate of the past, and that there's the ability to decode different items that have happened in the past as well, and that the past has this characteristic compression, such that it's as if memory is organized on a log timeline. I'll come to some more stuff in a moment, but for right now, I think the next slide, yes, is arguing that the brain manages to accomplish something like that. In the time since we proposed these equations, which I'll show you later, actually, we discovered, we here meaning many other people, have discovered that the brain has something like a temporal basis set in many, many different regions of cortex, and also hippocampus and striatum, and it's all over the place. So I'm giving you a whirlwind tour of maybe 3 dozen papers here. So the phenomenon is referred to as time cells. When something interesting happens, like that clap, if it happens again and again, we find cells like in A over here, where the cells fire as if they have receptive fields in time, right? They fire as if they're coding for that clap was 1 second in the past, or that clap was 3 seconds in the past, or that clap was 5 seconds in the past, something like that. Moreover, I said earlier that the timeline is not veridical, right? It's compressed. In B, you're looking at a set of 172 simultaneously recorded neurons with calcium imaging, and they're sorted on the time at which they fire within a 10-second delay. And you can see there's this characteristic curvature to them. And this is a consequence of there being fewer cells representing times further in the past, right? And for funsies, the dashed red line is the curve you would expect if the timeline was exactly logarithmically compressed. I'm showing you C from Bolkan et al. To show you that this phenomenon is observed in many different brain regions and many different experiments. And in this particularly dramatic example, sequences in medial prefrontal cortex go out to 60 seconds. We actually don't know the upper limit. And since this proposal, we've discovered a number of things about these time cells. We know that different stimuli, clap versus a chirp, trigger distinguishable sequences such that we can decode what happened when in the past. And we've now seen, we here again, meaning not me, mostly, have seen sequences in hippocampus, in medial prefrontal cortex, in lateral prefrontal cortex, in MEC, and striatum. Some beautiful work from Alana Witten showing sequences coming into the nucleus accumbens for people who are especially interested in dopamine. And so this turns out to be a pretty general phenomenon. I'm going to skip this, just showing you that we can decode what happened when. We've done this work and other people have as well. Okay, the point I do want to make here is that we're now becoming we're becoming pretty darn convinced that the compression is precisely logarithmic as best as we could measure. I'm pointing you to a paper by Ray Tao and Jay Bladen. Jay Bladen did recordings in Howard Eggenbaum's lab, and Ray's my postdoc, and she did some fancy schmancy hierarchical Bayesian analyses. The upshot of the paper, which should be going back out again soon, like Monday, is that the timeline is logarithmically compressed. And I think the best way I can argue this to you is by showing you the time cells ordered in linear time, and then also ordered as a function of log time. These are just exactly the same data. I've just changed the axis. And to the extent you see a straight line of constant width in time cells when ordered as log time, that's as if that shows that I've managed to undo the curvature, suggesting that compression really is logarithmic. And mathematically, this is especially really profound, and it's had important implications in our deep learning work. What this means is that if the timeline is logarithmically compressed, then rescaling time amounts to just translating that representation. You'd say that the representation of time is scale covariant, right? As I change the speed of events, I clap faster or slower, or I say 7, speak really slowly. The system's able to recover from this distortion because it just amounts to a translation. Pointing also to this spectacular paper from unipolar brush cells in the cerebellum from Guo et al., which is like our data, only way better. And so so for a mathematical conference about math and neuroscience, it seems really non-trivial that the representation of time is not translation. It's not, the brain seems to have chosen to make this very specific transformation of time, and it happens to be the same transformation as the compression of space in the retina. The receptors are distributed logarithmically, and it's consistent with the Weber-Fechner law, the oldest quantitative relationship in psychology, that things are on a log scale. That's why we measure volume in decibels, for instance. And it's also consistent with the nonverbal number system, which we know from Gallistel and Gellman and Liz Spelke and a bunch of other people, Stanislas Dehaney, that when we're not able to count and do actual thinking math, number is distributed on a logarithmic scale. Neither, lots of people have shown that. All right, so we proposed a formal model, and I think I have to go into this a little bit. Actually, well, this audience would like this sort of stuff. So our goal is to take a veridical past leading up to the present at each moment, and then maintain a memory of that with these specific properties that we desired to fit psychological data, and that the brain seems to agree with. So we're in good shape. And the only thing we could think of at the time, and in retrospect, this has become, really, in retrospect, this has become an increasingly good idea. But at the time we just wrote it down, it was the only thing we could think of, was that the brain should maintain as an intermediate representation in between the true reality and our estimated reality, the real Laplace transform of the recent past. So let's write this down. And then to estimate the past, you'd attempt to invert the Laplace transform, thus getting something that looks like the true history. So true history comes in moment by moment by moment at each instant, is used to update in real time real Laplace transform of the recent past, and then you use that to try and pull out the estimate of the past. And so the equations for real Laplace transform are trivial. You just have a bank of leaky integrators. For every what, you have a bank of leaky integrators with a continuum of S values, a continuum of rate constants. Each of these stimuli, when a clap happens, they turn on and then they deactivate, but critically they deactivate at different rates. If we solve that differential equation, we see that this f of s with the activity written across this set of cells indexed by s holds the real Laplace transform of that function we're trying to remember. And then if we choose the rate constants in a geometric series, we get this logarithmic compression. Just falls out, and there's a bunch of different ways to do that. So to invert the Laplace transform, there's a bunch of ways one could do it. It's sufficient for us today, at least, to imagine a linear operator called the post approximation that just requires taking derivatives with respect to s over here. And when you do this, it turns out that the receptive fields you get in that representation are unimodal and have the same shape as a function of their time constant. So the time constant of our estimate is, as one might expect, 1 over the rate constant, and you're taking derivatives with respect to the sheet in a neighborhood. And as a consequence, you get out this logarithmically compressed timeline, very much like sequential time cells. And we wrote all this down before this was known about time cells. We were pretty happy. It's serendipitous that worked out. I'm going to create a visual language as you go read neuroscience papers so that you can see this. So if I on the left, I'm just writing out the equations. So the clap happens, take a delta function at time 0. There's a set of the Laplace transform cells are all stimulated. They're all perturbed as the stimulus happens, and then they relax at a variety of rates. And the time cells in F tilde fire sequentially with receptive fields of that shape. Neuroscientists like to show all of the neurons in a heat map. And so I'm doing the same thing here, in which I've sorted the cells on their rate constant, and you get a peak thing. And I already showed you this for time cells. And I should add these ideas in retrospect were anticipated by many, many, many people. It seemed new to us, but that's just because we hadn't read enough papers. All right. So for about a decade, I mentioned we've seen time cell paper after time cell paper after time cell paper. We were really, really encouraged. But for a long time, for like quite some time, there was no evidence the Laplace transform part, which turns out to be critical for a number of things. And we were starting to get worried. And in 2018 or so, some things changed really rapidly. First, Albert Sal, working in the Moser lab, published a Nature paper, which I'm referring to here. And at the same time, actually, he was presenting at SFN. I also saw this data from my friend and collaborator, Elizabeth Buffalo's lab. It looks just exactly like Laplace transform. I'll take a moment and talk about our data. Miriam Meister and Beth Buffalo's data. Something interesting happens. In this case, the monkey is presented with a picture of actually just random pictures. There's a variety of pictures that are presented every so often at time 0, and the cells perturb. Most of them turn back off, and some of them turn back off a little more slowly, and some of them turn back off real slow, right? And so when you write them out, you fit a model, and you try to estimate their time constants, and you sort them on the time constant. You get out something that looks very much like a real Laplace transform of the recent past. I would add, since everyone's interested in deep networks all of a sudden, for good reason, that this is just a diagonal matrix, right? That the recurrent matrix you need to maintain real Laplace transform in the past is just diagonal, and this sidesteps a lot of the problems that people have with RNNs. I would also add that since I've been making a big deal out of this, a bunch of people have told me they're seeing stuff, and so I'm optimistic that there'll be other papers from other brain regions in the next couple of years. I don't want to steal anyone's thunder, but I'm pretty optimistic that this is going to pan out, and we'll be in good shape. So to summarize this, what we know about the past, okay, there is 100% temporal memory for what happened when in large swaths of the brain, not just the hippocampus, not just medial prefrontal cortex, not just striatum, but many brain regions, as if many parts of the brain are operating on information about what happened when to serve some function for memory or something else. We have pretty good quantitative evidence and at least some experiments that this timeline is logarithmically compressed in hippocampus and cerebellum, and the rest of it really looks like it too. These are just situations where people have really tried carefully to test it empirically. There's exponential basis functions, i.e. the real Laplace transform, and at least entorhinal cortex. And because entorhinal cortex provides direct input to the hippocampus, this idea that time cells are extracted from real Laplace transform seems at least plausible at this point. The major input to the hippocampus comes through the entorhinal cortex. Okay, hooray. And so this is good, and so brain has memory for the past. But we want to talk about the future as well, because that is in the title of the talk. That's what we said. So, all right. And so I think I haven't, so I'm going to try and talk about some ideas, and we're working out like a model where I think we've got it right, but I don't think it's quite ready to fit into a talk yet. And I don't quite have a paper. So I think I think we'll see how far we get in terms of talking about ideas, and then we might just declare victory and retreat for the day. The first thing I want to say is that there's a lot of work in reinforcement learning that's sort of built around the idea of prediction, right? And reinforcement learning, which I assume many people are familiar with, but here's the basic idea. Rather than attempting to construct the future, which I feel like we all did successfully in the introduction of this talk, right? Reinforcement learning adopts a strategy of trying to extract the value of a state, which is an exponentially discounted future value that one would expect to follow from this state. But it does so without actually explicitly estimating the future. It tries to use temporal difference learning to sort of note the change in the value that I was expecting, and use that as a gradient to build something that ends up estimating this exponentially discounted reward. Okay, because of this property, because of this Bellman equation underlying this, reinforcement learning is really well suited for Markov statistics, right? There's these beautiful results from Markov decision processes, but it also requires you to assemble discrete states. And so the idea we've been pursuing in a number of papers, and I think we finally got it right in this next one we're going to write out, is that rather than doing that, you just directly estimate the future, right? If you could somehow go A, and there comes B, if you knew that directly, you wouldn't have to have value that somehow bridges this gap, right? In some discrete, I wouldn't need to take that continuous interval and chop it up into states and then make the stuff go along. If I could just somehow figure out how we do that, we'd be in business. And this idea that temporal informativeness is important in conditioning, and many of the data that led to the widespread adoption of reinforcement learning is longstanding. And I'm particularly familiar with Balsam and Gallistel's work on this, and so this is a longstanding idea, and it was very inspiring idea. Okay, so how could we do this? Well, the first thing, and I'm going to do this in the context, I'll first make a note, make an observation between a really close correspondence between reinforcement learning and this Laplace transform of the past, right? So I said that the goal is to take Laplace, the past, and use that to learn the future. So the first point I want to make is that within reinforcement learning, from way back, I think this paper is from '88, the first introduction of the eligibility trace. These are equations from a paper by Rich Sutton from many years ago, and some that you maintain an eligibility trace in which you have this exponentially decaying record of the things that have happened in the recent past, and you use that to help you bridge gaps in reinforcement learning. And so if you write this out, this is called TD lambda, as an aside. If you write this out, you find, and you change variables, you find that this exponentially discounted record of the past is, lo and behold, has something like a exponential receptive field over time. So the only difference between eligibility trace, the only meaningful difference between eligibility trace and Laplace transform is just that there's a whole bunch of lambdas, right? So to the extent that there's already an exponentially decaying memory in reinforcement learning, the only change you have to make to adopt this strategy is to have a whole bunch of lambdas, mapping onto the s-axis. All right. So the basic strategy here is then to build a regular old associative memory, and I think I'm going to go kind of fast for the rest of this part, to build an associative memory between the present and the past. So B has a memory of Laplace transform of A tau seconds in the past. So if I go A tau seconds B, I get out and I probe this memory and ask what predicts B. The answer is A tau seconds in the past. Conversely, if I look at this associated memory from the other side and I probe it with A, I can ask what follows A, and I get out E minus S tau B. So after A, B will be tau seconds in the future, and that's the real Laplace transform of that. And this is sort of the basic idea, and I'm gonna, I think I wanna, in the interest of time, go really fast here. So if you take this seriously, what happens after B? So I present A, I get some estimate of the future, I have some Laplace transform of the future, and B is now, needs to come closer and closer and closer, right? I need to have exponentially growing cells, right? As tau goes, as the predicted time at which B is going to happen comes to 0, I need to have cells grow from E minus S tau to E minus S 0, right? And so this is a danger, Will Robinson. This seems like just a terrible idea. This just seems bad. And I also agree, that seemed really, really, really bad, exponentially growing stuff, until I saw the following data. So let's imagine, I'll just skip ahead. So this is data from interval reproduction task in medial prefrontal cortex. And interval reproduction, I go A, B, and then you have to do the same thing. You go A and B, only you're a mouse and you're licking or something like that. So in the time between A and B, you're remembering A was T seconds in the past, and you're also predicting that B is big tau minus T seconds in the future. And to the extent you accept that this on the left looks like the Laplace transform I showed you in internal cortex, and to the extent you accept the other population looks like a mirror image, you accept that there's Laplace transform of the time, both of the past and the future in this brain region. And I think I'm going to all the rest of this stuff. There's a bunch of things you have to work out, and we're working them out, and we don't have time to discuss them today. But to summarize, eligibility trace with continuous spectrum of lambda is from reinforcement learning is just the real Laplace transform of the past, which we've seen in entorhinal cortex. And so perhaps we can build a predicting of the future replacement for reinforcement learning that exploits these ideas, exploits the fact that we have a temporal memory in the brain to construct an estimate of the future. And preliminary neural data suggests that this is not insane. And perhaps the algorithm for constructing a continuous future from a continuous past is within reach. And perhaps that will be a paper you can read pretty soon. So to summarize, we know there's a temporal memory. As you approach reinforcement learning, there is memory for time. The Markov idea is not necessary. The brain has temporal memory all over the place. We have a ability to predict the future. The question is how. So, great, and that's my lab, and